let's give you two hints to the paper. The paper on page 19 gives you the connection of the used controllers to my writing in this document. You see the deadbeat controller is described in chapter 9.3, the deadbeat nu+1 9.3.1, the orientation controller chapter 9.6, the PFC completely starting with 9.7, and if you open the parameter box of the PFC parameter box, then you can see I have given you some information that you can find this controller described in this chapter, this controller, that, and so on. So this is, I think, help to get the correct simulation for the correct description in this paper. Another addition I want to show you as a curve in the paper is the disturbance behavior. We have done this still in previous experiments, but here last view on the disturbance response. Yeah, if you set the amplitude of your step to Z1, the controller have to remove the disturbance and set the output to 0. The desired value is 0, and you see the blue curve is the PID can do this, the red curve, the classical deadbeat can do this, the classical deadbeat nu+1 can do this also, but it's a little bit slower. The orientation controller cannot compensate the disturbance, and my version of the deadbeat controller also can't remove the disturbance completely. A known disadvantage, we have to discuss this point. And the light green curve is the PFC, which can do the job. So yeah, if there is a must, you have to select a controller. Here you can see the resulting disturbance behavior. Wait for chapter 9.13, then I can show you that I have worked on a disturbance compensation in my deadbeat by version. Then, yeah, with this addition, this can force also to 0, but I think that is a next week chapter. Okay, what I want to do today is I want to show you the theory of the PFC, the Richelieu controller type, if the process is not a PT1, not two PT1s, but if the controller type is an IT1. Okay, the principle is developed for a PT1. So he has a solution if you have a PT1 or a combination of several PT1s. Note that the left part here, the sum of two PT1s, is the way to adapt a two PT1 system. But why this is an IT1, I can show you in the next minutes. This combination is an IT1. Look what I have here. This is a PT1 in the feedback loop. So this is a feedback loop with a negative sign here and a negative gain here. So this is a positive feedback. What this is for a behavior, I can show now in the next step. Or in other words, I show you that this behaves exactly like an IT1. Let's do this in my OneNote writing. So chapter 9.8.2, this is a disturbance behavior. See paper. We have done this in previous videos and simulations, so this is nothing new. So what is new is 8983 PFC officially with IT1 processes. First, the question is this real? Is this necessary? What are examples for IT1 processes? Examples for IT1 processes are position control systems, position control, and tank level control. And you can imagine that a position control system very often appears in industry. Yeah, so there are many processes which has an internal integrator and some or more delays, not delays, but PT1 low passes. So we have finally an IT1, IT2, or IT3 process, but all these IT2 processes can very good simulated with an IT1 process or IT1 process with a delay. Doesn't matter. So the theory based on the PFC theory based on a PT1 design. And he has not developed a similar design for other types. So the PT1 design is complicated enough. If in the 2 PT1 series connection, we have shown that this can be changed into a 2 PT1 parallel connection, and then he can use 2 times his PT1 design. And similar way he has done with the IT1. I show you, I have copied the picture out of the paper, the IT1 paper, yeah. So is separated in 3 PT1s, and this should behave like an IT1. I want to show you that this is really true. So with these numbers, I will show you the total behavior. First, let's look for the right part, the transfer function of the right part. Right part. F of P is this is a loop, you see, a loop system. So we have the rule for completing combining loops, which is forward block is here a 1, and in the denominator we have a 1 with a minus sign here. We get a plus sign here, plus all loops, all blocks in the loop. This is a PT1 with a negative gain of -1 divided by a 1 plus P times time constant, in our case 0.05. Of course, it's true for for all other constants. This is a constant example. So what is this? This is I have to factor this out. This is 1 plus P in the denominator has to remove by multiplying numerator and denominator with 1 plus P times time constant. So we have in the numerator 1 plus P times 0.05, and in the denominator we have the 1 multiplied with this denominator is 1 plus P times 0.05, and finally with -1. So you see this +1, this is -1, remove themselves, and we have finally the following behavior. This is a 1 plus P times 0.05 divided by P times 0.05. This here is a PI block. Yeah, a PI block with a positive feedback of a PT1. Yeah, this behaves exactly like a PI. So this is my integrator with a PT1 and feedback. You can simulate a PI behavior. Yeah, we have shown this. So this is the right part FFP. Now this is just a sum. Yeah, we call this FL. The sum of two PT1s, and the transfer function FL is just the sum of minus 0.225 divided by 1 plus P times 0.03 plus 0.375 divided by 1 plus P times 0.05. Is common denominator is a product of single denominators, 3 times 1 plus P times 0.05. In the numerator, this has to be multiplied with this, so we have a minus 0.225 plus minus whatever, minus 0.225 times P times 0.05 is the left part, plus 0.375 plus 0.375 times P times 0.03. Okay, now we check what happens. This is solved into the following expression. Plus 0.375 minus 0.225 is 0.15. And the P times negative 0.225 times 0.05 plus 0.375 times 0.03 is, I have to start my calculator. Yeah, this part, this negative part here and the positive part here, they just have the same size, so there is no additional part in the numerator, plus 0. So we have now the total transfer function f total is fl times fr, and this gives, ja, machen wir weiter, bin gerade gestört worden. Let's look for the numbers. Here in the numerator we have the 0.15 divided by the both pt terms, 1 plus p times 0.03, 1 plus p times 0.05, and now multiplied with the right part is 1 plus p times 0.05 divided by p times 0.05. And you see here, because the coincidence of these both time constants, so this only works if these time constants have the same value, we can now wipe out this term with that term. There is a compensation, and finally we have the resulting transfer function. You see the 0.15 divided by 0.05 is just a factor of 3. 3 divided by p times 1 plus p times 0.03, which is exactly the IT1. In the paper you will see the IT1 is exactly has this term, the k of 3, and the time constant 30 milliseconds. Yeah. So this is a way to convert an IT1 into 3 PT1s, and then we can 3 times apply the design of Mr. Richalet, and then put all these together, gives the resulting term we will show in the next steps. Note here we have a time constant which finally is compensated. So in the behavior, this time constant plays really theoretically no influence. So this is a free choice. Yeah, you have a free choice of this time constant, but Mr. Richalet recommends in practical applications should this time in the near of our 5% settling time. Yeah, mathematically doesn't play any role, but in real circumstances, recommendation, this free selection of additional time constant should be in the near of the 5% settling time. Okay, this is a way I have shown the combination that this behaves like an IT1. Now we have to look for a way to convert an IT1 into this structure. Yeah, this is the step you can find now in my paper. Here in the in the paper you can see what happens. First we have a free choice. We call this T-deck. T-deck is the free choice 0.05 in our example. T is the time constant of the IT1, our 0.03. K is the PI time constant, PI gain, yeah, our 3 in our application. So here you have K2M value, which leads then to, I think, this number. K1 is this number, and this is -1. This is T-deck. This is T-deck. This is our time constant. So this is a equation where you can calculate this both PT1 gains. So this is a way to convert any IT1 into a PT1. Should I write this down in my paper? I think I should do this. Yeah, IT1. This symbol IT1 with a KI and a T time constant is converted into the sum of 2 PT1s, where the output now is added, and this is PT1 number 1, PT1 number 2. This is called then K2M, this is K1M, this is T, this is T-deck, and here we have our feedback, PT1, was gain -1, negative feedback, so in total positive feedback, there was T-deck. So T-deck, free choice, recommended, equals TC. This T comes from this, and key K1M and K2M, see paper. The equations in my paper, so I think here we have the equations. I copied this in my paper, sorry. Yeah, here you can see the copy of these elements. K2M is this expression and K1M is this expression, and if you take these examples, then you can of course calculate these values with and you get finally these numbers. Yeah? So this is a way to get the two gains of the PT1s, and here is feedback, and the PFC equations now are changed in the following way. You see on page 93 that here we have the equation to calculate step by step, sampling point for sampling point, the new y of k, the controller output. For this we need three coefficients, a0, a1, a2. Then we need our desired value w. We need an intermediate value CV predicted, controlled value predicted. Here this is a model output of my PT1 number 1. This is model output of the PT1 number 2. This is model output of the PT1 in the feedback loop. And again, this is the CV predicted value we have here. Okay, how can we calculate the CV predicted? Desired value, process model output 1, 2, 3, negative 1, 2, 3, but now delayed. So this is just again included the Smith predictor trick, yeah, with a delay button. With a delay of your process. Here you can calculate the model output values of the three PT1 models. And here are the calculations of the well-known three coefficients with similar expressions. Here you see the lambda value, which can be calculated with the 5% settling time. Here are the case of the model values we have calculated just before. The ace here depends on the time constant, and this just a list of equations where you can find a way to calculate model outputs and coefficients, and finally lambdas and CV predicted value, and finally this equation for the controller output for my IT1 process. Yeah, the way I have looked for the solution for this IT1, I can say in the book, there, the way to find out these equations takes 3 pages. I worked several hours on the theory behind these equations, and the problem is in the book, in that edition I have, in this book there are some errors, so I get different equations than this. But in the book also Mr. Richelieu has presented a MATLAB code where he calculated exactly these equations, and there are the differences between his theory and the MATLAB code, so that I have looked for the correct equations here, which fits to his MATLAB code, and which I have programmed in my C# code, which works properly. So his theory has to be updated or corrected. I think, yeah, happens also with maybe he's rather old man. I think he was in the 80s as I met him. Yeah, so he's rather old man. Okay, let's look for practical results. Yeah, so I think now we have to go to my simulation and look how this IT1 PFC really works.